Hi, my name is Tucker Hayden, and I'm a navigation engineer at Sandia National Labs and a PhD student at the University of Texas at Austin. My colleagues, Andy Huang and Todd Humphreys, and I, are excited to share with you some recent results on the radar navigation algorithm we've been developing entitled Trusted Inertial Terrain-Aided Navigation, or TITAN. Specifically, our analysis has revealed some key performance properties and explained some curious behaviors observed in previous work. These results are published in the companion paper to this video abstract. Let's jump right in. First, some context. We introduced the TITAN algorithm at the 2023 ION GNSS Plus conference. If you're unfamiliar with the concept, I suggest you take a look at the conference publication, which describes the algorithm in full. A quick summary. TITAN was proposed as a method of achieving multi-beam radar navigation performance using single-beam hardware. Specifically, TITAN leverages a vertical synthetic aperture radar mounted on an airborne vehicle and makes closest range measurements to ground feature points along prescribed iso-Doppler contours. We call these measurements minimum range prescribed-Doppler, or MRPD measurements. Similar to other terrain-aided navigation algorithms, these range Doppler measurements are correlated against a digital terrain elevation map within a nonlinear Kalman filter to estimate the radar's position and velocity. The MRPD measurement function, however, is different than most other measurement functions in that it is itself a constrained optimization problem. The measurement is defined as the minimum range along a prescribed, hint, constrained, iso-Doppler contour. The range is minimized and it is subject to a ground constraint and a Doppler constraint. This constraint optimization property of the TITAN measurement function made it difficult to implement the measurements in an extended Kalman filter. For EKF integration, the Jacobian of the measurement function with respect to the position and velocity of the radar is needed, but it was unclear how to compute the Jacobian of a constrained optimization problem where both the cost function and the constraints depend on the state. Prior work avoided this problem by computing the Jacobians with a finite difference cubature transform method, enabling integration into an EKF. Numerical finite difference methods, however, yield little insight into why the algorithm behaves the way it does, and they preclude other first-order analysis, such as Cramér-Rao lower bound performance analysis. This publication tackles this lack of analytical Jacobians and general lack of analysis. First, we found an analytical solution to the MRPD optimization problem by casting it as an optimization problem subject to conic constraints. We were then able to derive an analytical expression for the MRPD measurement function, the associated Jacobians, and the Fisher information matrix and Cramér-Rao lower bound on the estimation error covariance. We validated these expressions with Monte Carlo simulation, and we found a fundamental performance difference in the along track and cross track directions. Finally, we showed that the performance difference stems from an asymmetrical application of the Doppler constraint in the along track and cross track directions. All this and more is available in our publication. We hope you enjoy it.